Hello and welcome to the Diamond Steel Frames webinar. My name is Dorothy de Pauw. I'm the Sales and Marketing Manager at BuildSoft. Today we are going to show you how to set up a 3D steel frames, including the connections. But first, some words about the company. Well, we have over 2,000 customers who use our software in more than 50 different countries in the world. We have over 26 years of experience in structural design analysis and design codes. There are over 4,000 licenses in use with our customers, and 3/4 of the Diamonds customers have maintenance or subscription contract. That means that they are active users. And every year there are about 2,200 student registrations for a free educational license. So the research, the development, the sales and support are all located in Belgium. We are in Ghent, which is a very beautiful town. And we have resellers in over 20 countries all over the world. Now about the product Diamonds. That's what we are going to talk about today. It's very easy to use finite element software. So we always start with geometry, then we will add loads, we will generate the mesh, the finite element mesh, and then we will look at some results. So with Diamonds, you can do the analysis and design of 2D frames, 3D frames, floor slabs, walls, plates, beam grids, and complete 3D structures in steel and in concrete. We support different materials. We have the design codes for Eurocode 2 to concrete. We have the steel, we have timber, and of course, not only Eurocode, but several design codes are implemented, and we also have the possibility to choose between different languages. Now, for the example today, this is the model we are going to create. It's a 3D steel frame building with wind braces and connections designed. We are going to create this building starting with a 2D model, which will then be expanded to the 3D model. Now, when you are working on a real-life example, you can start, of course, directly with the 3D model. These are the details of the 2D frame. So the frame has a total width of 28 meters. So we have 22 over here, and we have a little part on the left side, which is 6 meters. The total height is 7 meters 45. The roof is an IP360 cross section, and it has a slope of 15 degrees. The main columns, which are over here and over here, are HA 280. The outer left column is also an HA, but 180. We suppose that there are purlins. The purlins are represented by these nodes in the first 2D example, and the maximum distance between two purlins is 3 meters. Now, how are we going to proceed in Diamonds? Before I forget, we will also consider some loads, of course, of the structure, which is the self-weight, the dead loads, the wind and the snow loads. Now, how we are going to proceed in Diamonds? Well, we have a general workflow. There are 4 main steps. So we have the geometry, the loads, the analysis, and finally the design. We always start, of course, with geometry. And here we will create the model by drawing in the software or importing it. We will assign cross-sections, materials, boundary conditions, supports. In the next step, we will define the load groups, self-weight, dead loads, and we will also define the load values, for example, 3 kilonewtons per square meter, and we also make the load combinations. So for Eurocode, that's ultimate limit state and serviceability limit state. Next, we are moving to the elastic analysis. We'll make the mesh and do also mesh verifications, everything okay with the mesh. We'll do the elastic analysis, and we'll take a look at some results such as deformation, internal forces, stresses, reactions. And finally, we will do Eurocode steel verification, so that is step 4. And here we will set the correct parameters for buckling and for lateral torsional buckling. And we also set the correct steel design code. And finally, we will, of course, ask the software to perform the steel verification or the strength and stability verification. And then we can choose to do an optimization of the cross sections, and there's also the possibility to do the detailed calculation of the connections. Okay, so let's get started now. I'm going towards diamonds. So the first thing I'm going to do here is set the language to English. Okay, so you can clearly see that our 4 workflow steps, they correspond with the main windows in diamonds. So we are currently now in the geometry window, but we also have a loads window, mesh window, and a results window. Yes, and each and every one of these windows have their own sidebar with tools and possibilities. Now, let's start, of course, with the geometry. And there are many ways to get this geometry modeled. You can either import a DXF file, or you can draw it, and I will choose it front view over here. You can draw it directly on the screen, something like this. For example, here we are, just drawing it directly on the screen, and I'm leaving the drawing function with escape. And then you can play around with the dimension of this little frame. So we can double click, for example, on a certain node, and we can set it, change the coordinates. We can also double click a line and modify the length. Now, however, for this example, I will use a structure wizard. So what I'm going to do is selecting this little frame, I'm going to delete it, and we are going to use today the structure wizard. So, and of course, our example corresponds the best with this one over here. So, for the roof, so we have a slope of 15 degrees. There are 3 intermediate nodes on the left and also on the right. The width of the frame is 22 meters. The cross section is not an IP 180, but I am going to choose another beam section. And here you have the possibility to pick one of these predefined cross sections, or we can use the library which has the most common cross sections built in. So it has all IP H sections, but also U beams and W cross sections. So it's an IP 360. Okay, I'm confirming again with OK. Now for the columns, the column height is 4.5 meters. So on this side. And the cross section is an HEA, going back to the library right now, an HA 280. Okay. And we have 1 intermediate node on the right side. The supports, so the left and right boundary conditions are just simple supports. Click OK to confirm, and the model is created by diamonds automatically. Now we will add the smaller part on the left side. So how will we do that? Well, I'm just going to create a simple line which is not even close to what we are looking for. Just drawing it and leaving the drawing function with escape. So now I will double click this line to edit the properties, and as you can see, there are 2 little blue parallel lines who appear, which means that at that point the mouse will snap to the line to double click it. So that's very practical. You can also see a similar phenomena when you are approaching a node. So let me double click this line. So when we double click it, we see a copy in this little window of the line. So what we can see, there's a little white square around point 13, which is this point. That means that point 13 will remain fixed and point 2 will move when I modify the length or the angle or whatever. Why point 13 and not point 2? Well, that is because I double clicked more close to point 13 than towards point 2. So, but that is not what I'm looking for. What I'm looking for is that point 2 will remain fixed and point 13 will move around. So what I'm going to do, I'm going to close this window and I'm going to double click more close to the other side, to the right side. Double click again, and now you can see there's a little square around point 2. So point 2 will remain fixed and point 13 will move around. So what are the values for this one? Well, we have a horizontal length of 6 meters and the angle is minus 15 degrees. Okay. And there we have the extra piece of roof. So the length of this element now is over 6 meters. Yes. Now we said at first that the maximum distance between the purlins must be around 3 meters. So this is way too much. So what I'm going to do, I'm selecting this element and I'm going to divide it in 2 pieces so that we have around 3 meters between the purlins. Now for the cross section, these 2 lines, currently they have no cross section. Of course, the cross section of these must be the same as the other parts of the roof. So what I can do very easily is select this one with the right mouse button, copy properties, select the other 2 elements, paste properties, section material type, and right now they also are an IP360. Okay, for creating the column right now, so I'm just going to create a line. I'm snapping again with the blue circle to this node, and we are just going vertically down. If you want to be sure that you're perfectly vertical, or that you're going down in a vertical way, you can always use for example, the shift button. I'm going to click over here and escape. So this little element needs a support. So what we can do, I can select the node and go to the supports dialog and choose a simple support. Or we could have used the copy function of this one, copy properties, paste properties, support. That will be also a possibility. Now the cross section for this column is an HA 180. So I'm selecting the line, the column, going to the library, and I'm going to pick an HA 180. There we are. So although I have assigned the different cross sections right now, you can only see the axis of the elements, but it's just a matter of representation in diamonds. We have the possibility to show also like the solid cross sections, and here we can see the different. Maybe it's better to see in 3D mode. Here we can see clearly the drawing of the different cross sections. So concerning the purlins right now. So we have represented the purlins with the intermediate nodes. Now, if you look at the model right now in 3D, and we would give a little push in the Z direction on this frame, just a very, very little push, you can clearly see that the frame will fall over, will flip over. It's because there are no supports currently. However, within the 3D model, we can suppose that this frame is supported by the purlins. So what we are going to do, we are going to add supports to the purlins, to the nodes who represent the purlins. So I'm going to select all these different nodes. And I'm going to tell the software, listen, it's not possible that this frame can fall over because the purlins will prevent that. So I'm going to do the supports dialog. Here we can check. The Z displacement is not possible, is fixed. You can see a little red line. I'm clicking OK. And if we go back, if you can see, the little red lines are present now, and they are representing the supports of the purlins. Now, finally, and I'm going back to front view, finally, we will add some haunches for the global analysis. This is, of course, optional, and you should only add them if you know for sure that they will be there. So I'm selecting bars, so I'm going to add a haunch over here, 2 over here, and 1 over here. So the definition in diamonds is either at the end of the bar or at the beginning of the bar. So I'm selecting these two. So I'm going to add one at the end of these bars. And for that definition, I'm going to the end releases and bars. And here, conditions at the end, just checking haunch. Now, as we are not detailing in diamonds, we only need to enter a length. And the length is 1 meter, and a height, like that. So the detailing, we will do the calculation of these haunches later on in Power Connect software, but in diamonds it's just a global analysis. I'm selecting these two, and I will add a haunch now at the beginning of these 2 bars. Haunch 1 meter, 40 centimeters. Okay. Now we have defined these haunches, and let's take a look in 3D. I'm just going to show you this element only. And as you can see, the cross-section of the haunch is tapered, of course, and it's taken equally as the cross-section of the beam minus the upper flange. So the details of this haunch in the global analysis are not that important, but we will do the verification later on in the Power Connect. I'm putting everything again visible and wireframe mode. And I think with the definition of the haunches, we can conclude the geometry. And now we are ready to move on to the loads. So for the loads, this is the second step in the workflow. I'm moving on to the next window in diamonds. The first step here is telling diamonds what load groups to consider. So we can do that over here with this safety factor symbol. So we can set the different load groups over here as well as the design code. So the load design code for today is Eurocode 0, and Eurocode 0 is also known as EN 1990. But we also have implemented, for example, American code and many others. Now, for a real life example, you should also choose the proper national annex. Yes, and this can be done in this drop-down box. Now, because we have a mixed audience today, I will not choose a national annex, but we will calculate using the general Eurocode regulations. Now, on choosing the correct design code, diamonds will automatically adjust the safety and combination factors, which are over here. You can also play with the consequence class and the design lifetime. You can immediately see when I change the consequence class, the safety factors will increase or decrease. So today we work in a very standard situation, which is consequence class 2 and a design lifetime of 50 years. We will consider 4 load groups. So we have self-weight, dead loads, wind, and snow. Now the self-weight and the dead loads are already present, so that is good. We only need to add wind and snow. So I'm going to add 2 load groups, which are currently called 3 and 4. But as you can see, the safety factors and combination factor are all at 1. So looking at the self-weight and the dead load, you can make up for yourself. Okay, that can't be correct. Once you add a new load group, you need to pick the correct type out of the predefined list we have over here according to Eurocode. So for load case 3, I will choose wind, and for load case 4, I will choose snow. And you see immediately once I check the correct type, once I select the correct type, the safety factors and the load combination factors are set correctly according to Eurocode. Now for the wind and for the snow, Eurocode 1 describes different cases. For example, there can be a wind from left to right, from right to left, from front to back, etc. In total, for this simple frame, we have 20 different cases to consider for wind and 3 for snow. So what I could do is make another 19 load groups for wind and 3 for snow, and tell the software that they are not compatible with each other because either the wind is coming from left to right or it's coming from right to left, but not two together. But I'm not going to do that because that's quite a lot of work. So I'm going to delete these extra cases. What I'm going to do is use an option in the software which is called subload cases. And when we check this option, you will see that the software will create 3 extra columns. The first one is the number of subload cases you want to consider. So 20 for wind and 3 for snow. In the second column, we have the type, and you can set over here if the loads are always together or never together. So if they are compatible or not compatible. So when we click the button, you will see that this symbol, 2 persons giving each other the hand, they are always together. Excuse me, always together. So this is not the case for wind loads. For wind loads, they are not compatible with each other. They will never be together on the structure. So we must choose the other option. Let us take a look at snow loads. This is already set correctly, so I think the definition is fine right now. In the third column and the last column, of course, you can give a name for each subload case. So we are not going to do that today. I think that's not relevant. So we're confirming the settings with OK, and we will leave this window. Now we are entering the second part of the load definition, which is adding the correct values on the structure. So we have over here on the left side our different load groups. So we have the self-weight. Now the self-weight is generated automatically as all cross-sections and materials are known by diamonds. The dead loads, well, for the dead loads, I am selecting all the roof elements, and I'm going to add 3 kilonewtons per running meter. Yes, okay. So normally you should be able to read the numbers quite well, but if you prefer to have them a little bit bigger, that's no problem. You can play around with the font size and the symbols and the representation of the loads if you like. Also, you know, I have 3.00. If you prefer not to have as many numbers, you can set this over here, units and decimals, and you can set this, for example, to only 1, and we have the representation. We have another representation, so you can really customize in the software. Moving on now to the wind and to the snow. So for the wind and snow, there are 2 possibilities. Either you can determine the values of the wind loads and the snow loads yourself, or you can use the built-in wind and snow generator of diamonds. Of course, we are going to use the last one to generate 20 different wind loads at once, and 3 different snow loads also at once. Now, please remark that I'm not going into detail where all the 20 load cases for wind come from. You can find the full explanation in Eurocode Eurocode 1 part 4 for wind and Eurocode 1 part 3 for the snow. First step for the wind is setting the correct standards and setting a correct reference wind. So these are the settings for the wind generator. So the standard is Eurocode 1 part 4. And again, if you're working real life example, you should set the correct national annex in the next drop down box. Then we have to enter some values. We have a structural factor, a direction factor, and a season factor. The two last ones are usually set by the national annex, but in most cases, these three are equal to 1. That leaves us with the definition of the setting of the wind velocity. Either you fill out a value yourself, or you choose one of the built-in countries, open the map, for example, Belgium, opening the map of Belgium, and you choose the correct region. And finally, we'll have to choose the terrain type. The terrain type is something that takes in account if there are a lot of high-rise buildings, or if it's like a more open area. So for this one, we will pick terrain type 3. Okay. So right now, Diamonds has a reference wind that will blow over towards the structure that we have. Step 2 is a very easy one. Select the whole frame. And the third step for the wind load is putting the correct wind loads on the structure. So we use the wind generator for that. As you can see, the software recognizes immediately the contour, the form of our frame. And now, in order to be able to calculate the wind loads, we need to provide some extra geometrical parameters to software. So first of all, what do we have over here? We have total width of the construction, 28 meters. So that is from point 1 towards point 2, which is correct, of course. Then the total depth of the construction. Well, here, this is a front view, and here we have a top view. Our frame is over here, and the question is really, what is the size? What is the length of side left or right? Let us assume that it's 30 meters, and we'll put the frame halfway, 15 meters, and the distance to the frame in front and in the back is 5 meters. So this is already preset correctly. And here we have our 20 different cases. Then we say, okay. And I will set the font a little bit smaller. As you can see, Diamonds has created 20 different, I'm walking through the 20 different cases right now, 20 different cases of wind loads. For the snow, it is quite similar. So first of all, we will set the correct standard for snow, which is Eurocode 1 part 3. Again, if you are working on a real life example, you set the national annex over here. So if the country is not determined, we can choose, for example, the Central West Zone in area 3. Then we have to enter an altitude. The altitude is really the height above sea level, for example, 10 meters. And this is the snow load at the ground that is calculated as about 42 kilograms per square meter snow load at ground level. And the exposure factor and the thermal factor, these are normally set in the national annex, and mostly they're also equal to 1. So that was the first step in the snow load. Second step is selecting the whole frame, very easy. And third step is using the snow generator. So again, the frame is recognized by the software. This frame takes on 5 meters, so 2.5 from the frame in front and 2.5 from the frame in back. And we are going to consider 3 different snow loads. So this is the first, second, and a third. So the loads value definition is done. So in this last step in the loads, we are going to let diamonds generate load combinations, which can be done over here. And we ask diamonds to generate them automatically. So that means that the software will make all possibilities of combination of loads for ultimate limit state and serviceability limit state, according to Eurocode, of course. So I want to see the different load cases, also ultimate limit state fundamental combination, and the serviceability limit state, the rare combination. Okay, so these are the different load cases, load groups. We have the ultimate limit state, 20 combinations. But of course, keep in mind that it's not just 20, but it's 20 ultimate limit states multiplied by 20 wind loads and multiplied by 3 snow loads. And finally, we also have the serviceability limit state. Okay. So the load definition is now done. We are ready for the analysis. So we are in the workflow now in step 3. So diamonds is a finite element method software. That means that every bar, every plate in the model will be chopped up in a number of little pieces or elements necessary to be able to calculate the structure. So the user can decide on the size of these pieces or finite elements. And he can do that by choosing the mesh parameters. And we can set the mesh parameters over here. Now for a frame structure with no plates, so this is what we have right now. There are no plates in this model. Only the 2 items below the horizontal line are relevant. So the question is very simple. In how many pieces should each bar be divided for analysis? How many analysis points do you want for each bar? Usually 8 divisions is just fine. Okay. So diamonds calculates the mesh, and we can also visualize it over here. These are the different mesh nodes that you can see. Let us move on now to the calculation. You can ask the analysis by clicking on the calculator button. So although that diamonds has a second order option, it's wise to start with a first order analysis. So we click OK. Once the calculation is done, we are automatically moved over to the results window. Here we can find deformations, reactions, stresses, internal forces such as bending moment, shear force, normal force. And we can find these results for each and every load group, load case, so the sulfate, dead loads, winds, and snow, but also, of course, for the ultimate limit state combination and the serviceability limit state combination. Diamonds has also made an envelope result, which is an assembly of all minimum and maximum results of all the 20 load combinations ultimate limit state. So what we are looking at right now, the envelope, it's not a real state of the structure, but it allows the designer to easily identify the critical points. You can also select one or more elements along the same line and have them shown in a separate window for detailed view. We call that detailed results window. This allows you to have a closer look at what is happening in these elements. With the slider on top, you can walk along the axis and see the results at each position. You can even fill out a distance, let's say 4.5 meters. and the slider will snap to this distance. We'll close this now. Finally, you can also take a look at the stresses, and we can double click an element, stress results. I'm not going to choose the envelope, but the first fundamental combination, and we can walk along the axis. You can fill out a distance, and we can zoom in and out in this window, and you can walk over the cross section and see the variation in stresses at a certain point of your choice, or you can just walk around. Okay. Now, looking at the stresses and the global results, we can already have some idea whether or not the cross section is chosen well. Because, that is the question, of course. Are the current cross sections okay? Yes or no? And to get an answer on this question, we need to perform the steel verification. So at this point, I think we are maybe a little worried because we have a yield strength of steel of 235, and our maximum stress right now is 206, but we will see. So we are now in the fourth and final step of our workflow, which is the design. In this step, the material and the appropriate design code become relevant. So the first step over here is to choose the correct design code. We can do that with analysis, steel design code, and because we have set the loads, the wind and the snow according to Eurocode, we will also choose here for Eurocode with no national annex and method 1. Now, the Eurocode steel verification consists of 2 parts. The first one is a strength resistance check, and the second part is a stability check. Now, the strength check is performed on cross-section level, and it verifies if the current cross-section can take on the acting normal forces, bending moments, shear forces, and of course a combination of all together. Now, Diamonds has all necessary information for that check. The user does not have to do anything else, anything more. Secondly, we have the stability check. So this is a check to see if the column or beam will not fail as a whole due to buckling, which is normally caused by normal force, or lateral torsional buckling caused by bending moment, or a combination of both. So we have to work on the stability parameters. Let's start with the buckling, which is caused by normal force. There are 2 ways for the buckling, and I'm returning to the geometry window. There are 2 ways for the definition of the buckling. You can enter yourself buckling length, so you can select an element and go over here and select and set the correct Euler buckling length. Or you can choose to let them be calculated by Diamonds. And the calculation is based on the buckling groups. What is a buckling group? Well, for example, we have divided this roof element into 4 parts. Will they be able to buckle together? Yes or no? So Diamonds must know that in order to calculate correct buckling length. But Diamonds does not know automatically which bars are able to buckle together. So that is something that you as a user have to tell the software. For that, we have in the software two groups. We have buckling around the Y prime axis, so that is in-plane buckling, and buckling around the Z prime axis, which is out-of-plane buckling. Let's start with the first, and I'm going to select the solid mode, and let us also, yes, with the little red eye next to the configuration, I can choose to show me certain information on screen. So I'm going to check here the local coordinate system, which will show me the y prime and the z prime axis of each element. And I'm going to a 3D view. So for buckling around the y prime axis, what I can see over here is that these elements are grouped together. That means that when they should buckle to the left or to the right, they are acting together as a whole, which seems logical also for these elements. When they could buckle to the top or to the bottom, they will behave as a whole, as one element. And I think for the other elements, the definition is okay. When we look now at buckling around the Z prime axis, that is out of plane buckling, so that means to the front or to the back, these elements are considered separately of each other, which is okay because we have the purlin definition over here, and the purlins will act as a buckling support. It seems okay. The only thing I have to check is this one over here, this extra element, but there is also a purlin support. So what I'm going to do is select these two elements and degroup them. So that means that buckling is only possible between these two supports. So the definition for this is done. It's just very important that you check this every time if the settings are correct. And over here is calculating the buckling length. Okay, in a front view. And of course, I can also ask Diamonds to show me right now the calculated buckling length on screen. So, and these are the buckling lengths, and you can play again with the font size to set them a little bit smaller. That is for the buckling part. Now for the lateral buckling part, Diamonds makes an automatic assumption of the lateral buckling restraints. So we can show this also on screen. Lateral buckling supports or restraints. So now what we can see over here is red circles on the upper flange and lower flange. That means if the circles are in red, it means that there is a restraint for lateral torsional buckling. And the restraint is provided by the purlin support, which is logical, which is okay. If you like, you can always select an element and play around with the lateral buckling supports. You can set it free or fixed like it is right now, whatever you like, or you can even add some intermediate lateral buckling support. So, okay, I think the definition is done for the buckling and lateral torsional buckling. We can now perform a steel verification. So, this is done with the FE button. And there we are. So, and we clearly see that we have new results, and the results consist of two parts. So we have the strength resistance check, and we have the stability check. So this one is at cross-section level, so you see clearly for each section the results, and this is really done on the whole bar level. So each one is expressed as like a work level percentage to a capacity of 100%. So to answer the question, is the cross-section okay, yes or no? Well, the cross-sections are sufficient if both strength and stability results are below 100%. Otherwise, you should choose another section or reinforce it, or you can use the built-in optimization of cross sections. So if we look at the results right now, I think we have a very, very small problem over here at the column, but I think if we choose the haunch a little bit better, we could resolve this. You can also double click a bar and you can see all the checks that have been performed for the resistance. This is the strength check, and the buckling, the stability check. I think we are ready now for the connection design. Just one important remark, if you really, here we are just a little below the 100%, but if you're really above the 100%, it's no point in calculating the connections because there's also a little check in the Power Connect. So you first need to have a good global analysis with the proper cross sections, otherwise there's no point in detailing. Now we are going to calculate two connections, this one on top, and the one between this beam and this column. I'm opening the connection design dialog, and everything goes well. The connections are recognized. This is a top connection, and this is the corner connection. So we need to decide in the first step which combinations to take along to Power Connect. It's not necessary to transfer all combinations, only the extreme ones are sufficient. So we take the extreme ones and let's calculate the connection now. On clicking on this button, we will go to Power Connect with the transfer of materials, cross-sections, loads, etc. And in Power Connect, we will choose a bolted end plate connection. And the 3D model is generated automatically. Now, of course, we cannot modify everything in Power Connect. For example, if I double click the beam, I cannot choose another cross section because this is set fixed by diamonds. But I can play around with the end plate thickness and with the bolts. So I can double click the bolts, maybe choose another bolt diameter, M16, okay, optimize the bolt positions. And let us now calculate it. So the calculation is similar as in diamonds. So with the calculator button, you can launch the analysis. So looking at the results, there's nothing that is marked in red, so the connection seems okay. Yes, we have the moment, normal force, and of course the moment combined with the normal force, so which has a unity check and which is lower than 1. Everything seems to be okay, and the connection is classified as rigid. Yes, and we also have a rigidity graph. So this graph is representing the real behavior of the connection. And once you are happy with the results, so with the results, you can close this window to return to the Power Connect. We can insert this one in the library. So I think this is top splice. Okay. And I'm going to insert it on the structure. That means that the rigidity graph and the strength of the connection will be assigned to the node. Now, for this one, again, selecting the combinations, only the extreme ones, and calculating the connection. It's a bolted connection with end plate again. So here we are. Now, let us first do a fast analysis to see how far we can get with the current elements. And we clearly see that we have a problem. So we have an applied moment of 250 kilonewton meter, and our resisting moment is lower, is only 215. So if we look at the work level for the combinations, then we can see clearly that the column web is very loaded. It's in red. It's the most charged element. So if we want to have a larger, a bigger resisting moment, we have to do something about the column web. So I'm returning right now to the geometry, and there are many things you could do. So I will select the column and click once with the right mouse button. And you could choose here to add a web plate or upper stiffener or lower stiffener. So I'm going to add a lower and an upper stiffener. And as you can see, these elements are added immediately. There's no need to enter 20 parameters. No, they are immediately there. We can calculate again. And we have now a resisting moment of 260, which is bigger, of course, than 250. Let us take a look at the moment combined with the normal force. Everything is okay. We have 0.99, but it's still smaller than 1, so that is okay. The connection is rigid. We have the rigidity graph. This is now the real behavior of the connection. And as for the previous connection also, you can get this little point out of the software, which is very, very nice. So I'm happy with the current connection. I'm going to close this, insert it in the library, CB, column beam, right? And I'm going to insert it on the structure. Now, when we do that and we click OK, all results will be lost because the node is no longer completely rigid, but has a real, rigidity diagram, a real stiffness diagram that needs to be used. So like I said, OK, insert on structure. The results are gone. If I return now to the geometry window, we can clearly see that we have over here the bending moment is no longer fixed, but it's a function, and the function is equal to the rigidity diagram that we had in Power Connect. Okay. Of course, we could calculate the other connections too, but I prefer now to show how to make the 3D model out of the 2D model. So the first thing I'm going to do is free this frame out of plane, because remember that we have added the supports out of plane to represent the purlins, but as I'm going to create the purlins now, I'm first going to remove these ones. Okay, supports are gone, and now I'm going to select the whole frame, and let's use the translation function, the translate function, which allows us to move elements, but also to make copies of elements. So here I'm going to ask 6 copies, and I want that the distance between the frames out of plane is 5 meters. And also I want to create connecting lines. That means that each point will be extruded to the next frame. Okay. So here we are. I'm going to select now the purlins. And the purlins, the cross section for these ones is square hollow section 100, 104. And this is hinged. The hinges are represented by red circles. So as you can see right now, each and every element in the structure is represented in blue. So we can't get a real overview of our connections. So what I'm going to do, I'm going to put the new purlins into a separate layer, a separate design type, we call it in diamonds. So selecting the square hollow section and going to type. So I'm going to delete these ones, add a new one, purlin, pink. Okay. So you can see they are now in pink. In 3D solid mode, it's much clearer that there are different types of elements in the structure, and I can also, with the control button and click once on one element of a certain type, you can select all elements. Moving on now to the columns over here. So what I could do is select create line and draw a line from each point towards the Y0 level. I'm not going to do that. I'm going to show you another possibility. It is selecting all the nodes that you want to create columns for. Also on the other side. I'm holding down the shift button. Okay. And I choose the extrude function, and I'm not going to extrude a certain distance, but I want to extrude to a certain plane. And the plane is perpendicular to the, if we look at here, the right bottom corner, is perpendicular to the Y plane. So I'm choosing a Y plane, and now I can just click on a certain point that has the same coordinates or has the same coordinates of the plane. Okay, and here we have all different columns created at once. I'm going to select them again with the control button. These cross sections are in HEA 180. Okay, I'm going to put them also in a separate design type. So this is end column, maybe type of green. No, this green, yes. Okay, I suppose that well, let's take first a look at the 3D color solid mode, and you can see over there that the columns are maybe oriented in a non-practical way. So I think the wisest thing to do over here is rotate them over 90 degrees all at once, and we can also add a hinge on top. Like that. So we have the hinges on top, and then we can put supports. So I can select with just going into a front view, I can select the columns in the different planes. I have selected all the points over here, but at the same time over there. And select now a simple support. Okay. So that leaves me with only one thing to do, and that is the creation of the wind braces. So I'm going to draw these directly in 3D. So going from this point, and meanwhile I can zoom in and out. Going to this side, going to that side. Now I'm just going to turn the model. You know, we have these little scroll bars which you can use to rotate the model. If you prefer not to use this, I can show you immediately another way. Here we are. So you can also use the shift button, holding the scroll wheel down and moving the mouse, and then you also have like a 3D orbit function. Okay, back to the wind braces. Select them then all. Going to the library. Let us check an L profile, corner profile, L55. Yes, and I was a little too quick, so I have to select them again. Cross section, because I'm assigning a new type. Cross layer, wind brace, in bright green. Okay. So we can copy this one together with this one a few times. And I want 1, 2, 3, 4, 5 copies. And I really want that this point will be going to that point. So, and we have now copied braces in a very, very fast and easy way. Okay, I think we're about done. Just one more thing for the wind braces. The wind braces usually are capable of only taking on tension, so we can define this one or set this one as a tie rod. And tie rods are represented by the little triangles in the software. So going to the load. So what I'm going to do in the loads window, because I only have a few minutes left, is thing you need to do really is verifying, of course, the wind and the snow loads. But in order to calculate this 3D model, I am going to delete most of the combinations, because the tie rods have like a very special behavior which takes a lot of time to calculate. So, and in order to keep within the time frame of our webinar, I'm just going to keep one fundamental combination. Okay, and let's calculate it. So as you have seen, we need to recreate the mesh because we have added certain elements to the model. Once you add elements to your structure, you need to recalculate the mesh, but that goes really easy. And so what we are seeing right now, that this first combination takes already some time, because and the tie rod behavior is a very special behavior. It's a non-linear behavior. So that means that we need to have a lot of iterations to be able to calculate this type of elements. And when you only have 2 minutes left, well, you need to make sure that they are worth their while. So these are again the deformations. We have the internal forces, bending moments, stresses, etc. And now we can perform a steel verification for all elements. And then we will see the results for the whole structure. Yes. So let us take a look now. Remember that we were slightly above 100%. For the columns, now we are for the stability check at 99%, because now we have used the real rigidity of these connections, and they can sometimes they can create a little, repartition, or they can take on a little less or more moment. So other elements in structure can take on then the extra moment. And we have the strength check, resistance check, which is also okay. So at this point, everything seems okay. And I think we are then at the end of this webinar. So we have calculated 2D model, the connection is a 3D model. Oh, there's only one thing I need to verify. That is, are the connections still okay? Because we have calculated them for the 2D model. Well, we have a connection verification included in Diamonds. And here we can have an overview of all connections which have been copied a few times, and we can see the results of each and every one of them. And here we can see that there's just one connection of all of them that is not sufficient, that is not enough. So what we could do is going back to Power Connect and we calculate them, or you can take a look, maybe this possibility to define some loads in a different way, or there are many solutions for this problem, which is also very limited. Okay, maybe I have still 2 minutes to answer a question. Yes, let me take a look. Yes, is it possible to do a seismic calculation for this frame? Yes, it is. You can define a seismic load on the frame. First thing you need to do is going back to the loads window, and we are going to add a load group for seismics. So here we are, seismic. So, and okay, the software is now telling you, please be aware of the fact that the current load combinations are no longer valid because you have added the load. Okay, I know, don't worry. And now let's take a look at the seismic. Yes, we can now define a seismic load according to, again, the most common design code. So we are choosing Eurocode. You can include a vertical component, apply quasi-static corrections. You have choose the option between two types of spectrums. The ground type, which can be rock, gravel, sand. The important class, or is it just a simple, habitation, or is it like an office building, or like public buildings, and it will increase the safety factor. Then behavior factors, for example, 1.5, which are described in Eurocode, and the ground acceleration. Usually for each country there's a little map with all the ground accelerations, for example 0.53. Okay, so here we have the symbol of the seismic spectre, and what I need to do right now, so I'm going to delete all combinations, and I'm going to select only the seismic combination. Oh yes, of course, I can't forget the ultimate limit state. So deleting these again. And for the seismic, we only have one seismic combination. So, and now we're ready to calculate again with the calculator. And as you can see, there's another tab active. So it's a dynamic tab. So in order to calculate this structure, the software needs to calculate the eigenvalues, and we will calculate the first 10 eigen frequencies. Okay, let's get started. So after the first calculation of the ultimate limit state fundamental combination, which is a static combination, which is going on right now. After that one, the software will firstly calculate the eigenmodes of the structure, and then diamonds will see how the response of the structure is with the seismic action that is taken place on the structure. So here we are in the modal decomposition. So the eigenmodes are calculated. And the nice thing about Dynes is that you can really see the dynamic modes, the eigenmodes, and you can play them. It's very funny. You see really what is happening with the eigenmodes. Now, of course, the question always remains the same. Are the cross sections okay? Yes or not? That is why we can, and I'm just going to select one in the top view, just selecting this frame, for example. And I'm going to request steel verification for this one. And when I double click now on this bar, you can see that the ultimate limit state fundamental combination is checked, but also the seismic combination is checked. And the fundamental one is still, the determining one, is still setting the end result, but both of them are calculated, and of course that is important when you do the seismic calculation, that you know that both are checked, and of course the maximum of the two will determine the cross section. So I think we are really at the end now of our webinar, so I would like to thank everyone for attending this webinar, and if you have any questions, feel free to contact us. We hope to see you next time. Bye.